Steinhauer here. Welcome back. We have in the previous video talked about how the energy source for the sun cannot be things like combustion or gravitational contraction, and that in fact it has to be nuclear energy. And in this video, we will try to break that down and see what it means and talk about what it is precisely that is powering the sun and why it's powering. So first, let's disambiguate some confusion that usually arises in the subject, because when you say nuclear energy, you mean very different things on the sun than you do on the Earth. So in the Earth, we are talking, when we say nuclear energy, about nuclear fission. This is the process of breaking up large atoms into smaller atoms. By the way, to start off, what is the difference between a chemical energy and nuclear energy? In a chemical process, you're not fundamentally changing the atoms involved. When you burn a piece of coal, you're dissociating the molecules that make up that coal and breaking them up or putting them back together. That is a chemical process, the creation and destruction of molecules. In atomic and nuclear physics, you're talking about either taking a large atom and breaking it up into smaller atoms, or taking small atoms and combining them together to form larger atoms, fundamentally changing the elements involved. So in nuclear fission, you take large elements like uranium and plutonium, and you break them apart into smaller atoms. And this is the process that occurs in nuclear power plants on Earth to generate electricity. In the sun, it's completely different. You're taking small atoms, in the sun's case, hydrogen atoms, smashing them together really fast, having them stick together, and that also giving you out energy. That's an important distinction. You have fission, which happens on power plants on Earth, and fusion, which happens in the centers of stars. Right, so let's talk about in order to understand how nuclear energy works and how nuclear fusion works, we need to remember our parts of an atom. So what are the building blocks that atoms are made up of? And so here's a little chart, and we'll talk about there's three things that make up an atom: protons, neutrons, and electrons. Talk about where those things are, what the masses of those things are, and what the charges of those things are. So if you remember your high school chemistry or physics class, protons are located in the nucleus, and neutrons are also located in the nucleus, the very center of that atom. And the electrons are not located in the nucleus. They are located in an electron cloud, which is many, many orders of magnitude larger in size than the nucleus of the atom. So this would be electron cloud. Now, I'm interested in the masses of these different particles. The mass of so you may know the mass of a proton off the top of your head. You probably don't know the mass of a proton off the top of your head. But if you use the right units, everyone knows what the mass of the proton is. In fact, if you use mass of proton units, then the mass of a proton is exactly 1, because that's the definition of a mass of proton unit. And you can look up what that number actually is. It's something like 10 to the negative 27 kilograms. But I'm more interested in knowing how the proton and neutron and electron relative masses are, right? So on the scale where a proton has mass 1, what is the mass of the neutron? It turns out it's very similar to the mass of a proton. It's not exactly the same, but it's about 1, to within 1% or so, right? Whereas the electron is much less massive. The electron is more like, I'll say MP just so we know what the units are here, mass of protons. The mass of an electron is something like 0.001 mass of protons. It's about 1,000 times less massive than the protons and neutrons are. So almost all of the mass of an atom is contained in the central nucleus. Analogous to all of the mass in the solar system virtually occurring at the center in the sun. Now, Charge is interesting. You may have heard of electrical charge. You can have things that have positive net charge and negative net charge. A proton is different than a neutron. They have this, they're in the same part of the nucleus atom, they have about the same mass. Where they vastly different is in their charge. So for instance, a proton has a charge of +1. It is a positively charged particle. A neutron, in fact, the very reason it's called a neutron is because it's neutral, has a net zero charge. There is no charge on the neutron itself. And the electron has a net negative charge. In fact, it has an electron charge of -1. And now this is where things are interesting, right? In the mass, it wasn't the case that the proton and neutron were exactly the same mass. The neutron's about one mass of proton, about one proton mass, but it's, varying by a percent or so. This electrical charge, there is no about. The proton has a charge of +1, charge of proton units. The electron in that same units is exactly -1. An electron is oppositely charged and exactly the same opposite charge as the proton has positive charge. And that's a weird quirk of physics. Maybe it's not a weird quirk of physics. Maybe matter has to be built that way, but it's not. It is important for how our universe works. So that's the refresher on how the components of an atom work in where they're at and how they operate. Okay, so we need to think about another force now. We've talked really only about a single force so far, and that was the force of gravity. And if you remember, the force of gravity, let's just write it down again, looks like this. There is some constant, let's call it G, times the product of the masses, m1 times m2, divided by their separation squared. And so if you had one charge m1 there and one charge m2 there, and you had them separated by some distance d, this would define the gravitational force that existed between these two objects. The electric force is the force that operates, for instance, believe it or not, when you try to bring two magnets together. It is the molecular forces usually that hold matter together. It is another very important force that we experience in our everyday lives. And in fact, in our everyday life experience, the gravitational force and the electric force are really the only ones that we have an intuition about, that we experience fundamentally on a daily basis, even if we don't know it all the time. So we can write down the electric force. It's going to look a lot like the gravitational force. Are you ready? There's some constant. Let's call it K. I'm not even going to write it down. Doesn't matter what it is. I'm never going to ask you to use it, but it's analogous to G. And now we've got the two charges, the charge of particle 1 times the charge of particle 2. Those are Q's divided by the distance between those charges squared. This picture is exactly the same. You've got two charges here, Q1 and Q2, and they're separated by some distance d. And the behaviors of these two forces are exactly the same. You've got a G, you've got a K, but it's just some constant. You've got the quantities that are really important for this force. In the gravitational force, it's mass. In the electric force, it's charge. And then it's a 1 over r squared law, 1 over d squared law. The further the force goes down as 1 over the distance between these two particles squared. So that's important. And this electric force works almost exactly the same way the gravitational force does, except that there's a couple of fundamental differences between the electromagnetic force and gravity that is important. Let's go back to them. First of all, one of the differences is that these numbers are different. It turns out that the electric force, this number is quite a bit larger than G. You might remember capital G is 10 to the negative 11. Well, K is significantly larger than that. So it turns out the gravity is much weaker. In fact, it's the weakest of all the forces. And you only get gravity being important on large scales because the sun and the moon are net neutral, right? There's no net charge. But if the sun were entirely protons and the moon were entirely electrons, then the electric force would be much more important and much more dominant than the gravitational forces. But since the electric force kind of cancels out, then the gravitational force becomes important on large scales. The other major importance is the signs of these components that make them up. Mass can only be positive, and yet force, this Q, can be positive or it can be negative. And this is important. And the sign matters, and the sign determines what the direction of this force is. And so this is important. So let me write this equation down again. Fe equals K times Q1 times Q2 divided by D squared. Q1 can be positive or negative. And the same is true with Q2, right? And so if both of them are positive, or both of them are negative, then when you multiply Q1 times Q2, you get a positive number. Q1 times Q2 being both positive, or Q1 times Q2 being both negative, both of those result in Q1 times Q2 being a positive number. That makes Fe positive. And the convention is that a positive force is a repulsive force. Now, if one of Q1 and Q2, sorry, my Q's are terrible, is positive, and the other is negative, then Fe is negative, and that is an attractive force. That is a force that's trying to pull things together. You have probably a phrase you've heard before, opposites attract and like repels. This is exactly comes from this concept. Two positive particles will feel a force pushing them away. A positive and a negative force will feel, positive and negative charged particle will feel a force pulling them together. So that's a fundamental difference between the electric force and the magnetic and the gravitational force. The gravitational force is always an attractive force. In fact, we really should have a negative sign on this force over here on this equation, because no matter what, M1 and M2 are always positive, but the force is always attractive. This is confusing when you're not thinking about positive and negative forces, but technically the negative force is the attractive force, and so there always needs to be a negative sign there because it's always an attractive force. The electric force, there is no negative sign there, and that's on purpose because positive like charges repel, and that's a repulsive force, and opposite charges attract, and that's a negative force. Okay, so we can think back to the atom. You might seem odd that atoms in a nucleus could even be there at all, right? Let's just go to a blank page here and think about the atoms in a nucleus. Let's think about, let's say, a helium nucleus. Helium-4 has 2 protons in its nucleus and 2 neutrons. Let's just draw that out. Here's the 2 protons. I'll put some pluses there. I'll put the 2 neutrons as being black. And so you've got 2 positively charged particles smashed really close together. They don't want to be there. The electric force is pushing them apart. If there weren't a third force to hold them together, you'd never be able to make atoms at all. But it turns out that there's another force that kicks in at very, very short distances that is stronger even than the force of the electric force. And that's called the strong nuclear force. So that's required to get an atom like helium-4, and it's going to be required to have protons stick together at all, because the first step in having fusion happen is 2 protons have to come together and close enough together that this force will turn on and they will be held there. I sort of like to think about this. If you've ever played air hockey, you've got a table that's got a frictionless surface, right? So you've got air pushing up through it, and a puck little moves through and will bounce off of other things, including other pucks that happen to be there. Now, these pucks happen to be like charges, right? So these pucks, even though they're moving together on this air track, might be both positively charged. So it's kind of like the opposite ends of a magnet, or the like ends of a magnet trying to push them together, except they're really, really strong magnets, right? Now, if you can get them close enough together, there's Velcro on these surfaces of these magnets that is strong enough that will hold them together if you can get them close enough. That's the strong nuclear force. But it's really hard to do. Imagine a really, really large air table, and you've got one magnet sitting there, and you have to get your other magnet moving fast enough that it's going to actually stick to this first one that you've done. And unless the magnetic force, in this case, the electric force, is really, really strong. So unless you have your initial puck going really fast, it's never going to get close enough to actually combine and form a heavier nucleus. So first of all, you have to get your pucks moving extraordinarily fast, like temperatures of 10 million Kelvin fast and above. And you might remember when we talked about temperatures before, remember the hotter a temperature is, the faster the particles in that gas are moving. And so how do you get things moving faster to be able to get close enough that you can actually have them merge? Well, you have to increase the temperature. And we're talking about 10 million before it's even close enough, before it's even hot enough that things are moving fast enough that sometimes, occasionally, they can get close enough to actually merge. And even then, think about this, you have to have a completely head-on collision. It doesn't work if there's a tiny little bit off, like this diagram shows. If they're a tiny bit off, they're never going to get close enough to actually have a merger event happen. So you have to both have these things going ridiculously fast and in opposite directions and in exactly the same way, so that every once in a while, once in a few billion years, you'll actually have any given atom interacting with any other atom in the center of our sun. So that's the challenge, and that's why it takes temperatures that are so high in order to make this happen on Earth. Sorry, not on Earth, on the sun. Make this happen on the sun. We can't have this happen on Earth. We're trying very hard, and if we can figure it out, it will go a long way towards solving our own energy problems. Okay, the other analogy I like to make here is a mini golf course. If you've ever played mini golf, you know the hardest holes on the mini golf course are the ones where the hole is at the top of a hill, and that hill extends downwards in all directions. That's sort of like what's happening here. If you want to take the gravitational analogy instead of the electric field analogy. So you've got a golf ball, and if you hit it a little bit to the right, obviously you have to hit it hard enough to get it up the hill. If you don't, it's never going to get up there. So once you get it fast enough to get up the hill, if you've got a little bit to the right, that hill is going to make it go to the right and you're going to miss the cup. If it's a little bit to the left, that hill is going to make it go further to the left and you're going to miss the cup. You have to get it exactly dead on and fast enough for it to get to the top and then fall into the cup. And that fall into the cup is basically the strong nuclear force taking effect. Now, imagine that your mini golf course has a hill that's Mount Everest, and your and the atom is a tiny little golf hole at the top of that. That's sort of what this is. It has to be going really, really fast, 10, 15 million Kelvin fast, and going straight enough that it goes all the way to the top of this mountain and falls into the cup without any slight deviation left or right. It's just really rare and really hard to happen, even in the sun where it's really dense and 15 million Kelvin. Fortunately, the sun's a big place. So even though any random atom will happen once every few billion years, on average, this is still happening a lot at the center of the sun. We'll get to those numbers in a minute. So this is how the sun actually generates energy. The net process is, this is the net process. We're taking 4 hydrogen atoms, bare protons, and combining them together to make 1 helium-4 nucleus. And this is going to give us energy in addition to a couple of other things. Now, I already mentioned that it took a temperature of 10 million Kelvin to even get 2 of these protons to come together at the same. You should be asking yourself, isn't it nearly impossible for 4 to come together at the same time? And the answer is yes, you're absolutely right. This has to be done step by step. And there's a 3-step process that usually happens in the sun to actually go from 4 hydrogen atoms to 1 helium nucleus. And so the next video, we'll talk about the specific steps and the specific processes that happen to take these 4 hydrogen atoms and make 1 helium atom, and then why that actually gives us energy out in the end. Okay, see you there.